So hello once again. This is Roger Koch Barr talking for the bioelectricity course in week 4, topic 6. In this topic we talk about equations for the alphas and the betas. But let's back up just a moment and say where we are. We are trying to explain the big deflection from active tissue into action potential. We saw that Hodgkin and Huxley performed a series of experiments in the giant axon of the squid. They expressed the result for individual ion channels in terms of probabilities. And the probabilities increased or decreased as time went by. And in particular, they increased and decreased according to rate constants that were called alphas and betas. The alphas and betas were determined experimentally from the squid, and that's what we're talking about in this segment. Before talking about the alphas and betas specifically, we need to go back and review what is the difference between Vm with a capital and Vm with lowercase. This is important because it comes into the way the alphas and betas are given to us by Hodgkin and Huxley and how they expressed it in their experimental results. It's not very hard, but it is confusing if you don't understand the difference. Vm with a lowercase, this Vm is measured against the baseline of the recording. So here, this much is Vm. So at point A, Vm is equal to 40. Now on the other hand, capital Vm is measured with respect to a voltage of 0. So at point A, this much would be capital Vm. So at point A, lowercase Vm, the voltage off the baseline is plus 40, while capital Vm, the voltage referenced to 0, is minus 30. Now obviously one is related to the other, so that we have, as a matter of mathematical fact, Vm relative to the baseline is capital Vm, the absolute Vm, minus the voltage of the signal when the waveform is at rest, Vr. Here's a few comments on why there is both capital Vm and lower Vm. Vm with the lowercase v is much easier to measure experimentally, because if you have the trace of voltage versus time, you can take that actual recording, mark the baseline, then mark another point, and just find the voltage difference. Whereas on the trace of voltage versus time recorded from the squid, there's not going to be any line for 0. The reason there is not any line for 0 is that the baseline 0, or that is to say the 0 value, is affected by the drift in the equipment. And measuring DC voltages in preparations such as the squid is notoriously difficult. So when you do try to measure capital Vm, it is often the case that it is affected, the measurement, by what is called DC drift, or in other words, for the value of voltage equal to 0 to move up and down the page a little bit as time goes by. Then I should call your attention to the fact that here I'm trying as much as possible to be consistent and call voltages that are measured relative to the baseline with a lowercase Vm, and the voltages that are absolute to call those uppercase Vm. I'm trying to maintain that difference consistently, and I hope I do it without making too many mistakes. If you take the world around us, the big wide world, I would say everyone in electrophysiology recognizes that sometimes measurements are given with respect to the baseline and sometimes they're given absolute. But the way they are denoted changes from one author to another. So they may or may not follow this lowercase capital VM notational difference. Now, in a minute, we're going to look at the actual alpha and beta functions, but let me give you a few preliminaries. As we said, the basic idea of the alpha and beta functions are to measure how fast, for the alpha function is to measure how fast the N, M, and H particles are opening. Or putting that a little bit differently, to measure the rate at which the probability is increasing. If you go to Washington, D.C., and ride on the metro train in Washington, D.C., one hears the phrase, "Doors are opening," each time the doors open. And in a way, that's a corollary. Alpha is telling us doors are opening, and here's the rate at which that's happening. In contrast, the beta function are telling about closing, and they're analogous to the subway saying, doors are closing. How fast is the probability that N, M, and H particles are moving into the closed position? In both cases, alpha and beta, these are quantities that have units, and as rates, the units that are used there are per millisecond. Now, they could be expressed in some other units, of course, but as Hodgkin and Huxley wrote them down, they are per millisecond, and most people have just copied the Hodgkin and Huxley expressions, so those are per millisecond too. The only thing is, when they copy the Hodgkin and Huxley expression, they don't always remember to copy the units. So you see these equations out there sometime as just freestanding entities as if they did not have units, but in fact they do. It's worth making a note that although the alpha and beta functions are expressed as equations, even though they are presented as mathematical functions, they are in fact experimental results. You might say a part of the genius of Hodgkin and Huxley is they took their experimental results and presented them to us as mathematical functions, which allows us all to use them again very easily by copying those experimental functions. It is also true that these values of alpha and beta are ones that are measured for squid axon. That is, they're not the right opening and closing functions for, say, electrically active muscle in the human heart. Those may have comparable functions of alpha and beta, but they won't be the same. Saying once again, the alpha is the turn-on function, and their beta is the turn-off function. There is an alpha and beta for each of the three probabilities N, M, and H. The fact that there is an alpha and beta for each of them leads people to think in their minds that these actual functions are probably pretty similar. Well, that's just not true at all. They're notably different, one from the other. Even when the expression looks somewhat similar, they really are quite different functions. That is to say, the values of the function at different values of VM changes quite remarkably from one alpha to another alpha to another alpha. Since there's a turn-on function for each of the particles n, m, and h, and also a turn-off function. Then altogether, there have to be 6 functions in all, and then indeed, that's what's given. So we'll be looking at the expressions for all 6 functions, putting them on slides, but then looking at them rather quickly. Now here's another little detail which has ensnared many people in the modern era. It is important to realize that when Hodgkin and Huxley did numerical calculations, they did their numerical calculations manually. And that meant that when they did the calculations have some singular points, some points where the functions are undefined, and they just fixed that up. To them, it was not a big deal because they knew the values that should go there, and they just put them in because they were doing it manually. They rarely even mention it. On the other hand, when one codes these functions for computer evaluation, as is now done most of the time, most alphas and betas nowadays come out of a computer program, you have to watch out for these singular points, and you have to be, in particular, sure that you code something in there to take care of the case where the denominator of the expression goes to 0, which from time to time it does. Finally, you have to keep in mind that the alpha and beta expressions as written are done in terms of VM, little vm, the value off of the baseline. They are not done in terms of capital VM, the value absolute. The reason for this historically is that Hodgkin and Huxley could not measure capital VM. Their equipment was not stable enough to do that measurement. The ability to do that measurement reliably has been developed in the 50 years since they did that original work. Therefore, they did what they could, that is to say, what they could most reasonably and most readily. They wrote the expressions based on the data they had, which were VM displacements relative to the baseline. We talked about earlier what the difference was in capital VM and lower VM, so you know what that is. Okay, so now let's look for the specific equations for alpha n and beta n. As you know, n is the probability that a sodium channel is open, or out of a large number of sodium channels, the fraction of sodium channels that are open. And the alpha function is given right here, the beta function right there. If we look at the alpha function in the sense that we were just describing it, we see that there is a point at which the denominator is going to go to 0, and in particular it's going to go to 0 when Vm is equal to 10. So when Vm is equal to 10, the numerator there is 0, the e to the power goes to 1, we subtract 1 so the denominator goes to 0, and all these other if statements here are intended to take care of that fact. The beta function, which does not have that issue, is right there. For alpha m and beta m, the expression is shown here for alpha, here for beta, as given to us by Hodgkin and Huxley, with this other code intended to take care of this special case that's present. And for alpha h and beta h, we are very happy to see that there's no special case that has to be taken into account. I should say no special case. So here we have the alpha expression, and here we have the beta expression. If you look at the actual expressions here for H, and you remember that Vm is always a positive number during an action potential, well, almost always a positive number. The voltage rises out of the baseline. And you say, what do these expressions mean in terms of the channel? You'd say, well, what alpha H is telling us, looking at this argument, is that as H goes up, alpha H goes down. So it turns on less and less the higher that Vm is. And conversely for beta, we'd say, if you look at the way that expression is going to operate, as Vm goes up, the denominator is going to get smaller and smaller. So as Vm goes up, beta H is going to go up. So the turn-off function is going to get to be higher and higher with increasing Vm. So you can see what the H channel is going to do. As the voltage grows higher, turning on grows less, and turning off grows more. So more and more of the H channels are going to turn off as Vm gets bigger and bigger. And indeed, that is what happens. While I am in this section of showing specific experimental details, I thought it might also be useful to put in a slide that shows the parameters that normally are present in Hodgkin-Huxley membrane. By normally are present, I put these in as values that Hodgkin and Huxley associated with normal squid axon function. So you can use them as beginning points. Here are the conductivities, and here are the Nernst potentials, and the resting potential is usually about 60 millivolts absolute. In this slide, I also have written in some other values which are interesting to think about in the context of various applications. If you ask in this tissue, what is it that changes dynamically? Well, what changes dynamically are the parameters Vm, N, M, and H. Here are some sample values for those. Done under the conditions, the stimulus currents are equal to 0. Here's another set of sample values. These are just put out as specific examples of two situations, and they're referred to later on in the sections of the course. Thank you for watching. We move on now and talk about how this whole plan comes together. I look forward to talking to you again in the next segment.